Let's look at the motion equations for simple harmonic motion. We did something very similar when we studied kinematics. We came up with equations for displacement, velocity, and acceleration as a function of time for cases where we had uniform acceleration. And those were the motion equations of kinematics. Now we want to do the same thing for simple harmonic motion. What I'd like you to do here, let me set up the situation. We've got an object right here that's moving around in uniform circular motion. So there would be a vector, a displacement vector from the origin for that particle as it moves around. And we could talk about a y component of that displacement vector. And what I'd like you to do is draw a graph of how that y component changes as theta goes from 0 to 2 pi, as it goes once around the circle. Okay, so try the rest of this question now. Okay, so hopefully what you said was that it would start with the y value would be 0 when theta is 0, and that key points would be at pi over 2, a quarter of the way around the circle, pi, and 3 pi over 2. The maximum value of that y component would be the full radius, and the minimum value would be in the opposite direction with the same length equal to the radius. And so by the time you got to 90 degrees, you'd be at that maximum value. It would come down to 0 as it went through pi, reach the minimum value at 3 pi over 2, and then come back again. So we get a function like that. And then you're asked to write y in terms of r and theta, and that should be fairly simple. If we just focus in on this triangle right here, you can see that we're looking for the opposite side of that triangle, and that would mean that y is equal to the hypotenuse, which is really the radius of the circle, times the sine of the angle. So that's the equation that I wanted you to come up with. Here's a quick visual that will show you how that works and how that relates to simple harmonic motion. If I press play here, you'll see that the y component is simply following the motion of the mass in simple harmonic motion. And we're getting a sine function. What we're going to need to do is, we came up with this equation, y equals r sine theta. But that's really all about uniform circular motion. And what we really want to do is switch to variables that are all about simple harmonic motion. First thing we can say is that this radius in uniform circular motion is going to be equal to the amplitude of simple harmonic motion. So radius is going to become amplitude. And the IB likes to use an x naught for the amplitude. The second thing is that y value. Well, typically we like to call this the displacement vector. So our y in uniform circular motion, the y component, is going to become the displacement vector in simple harmonic motion. And the other thing we're going to have to do is get rid of the theta, and it's going to become, we'd really, in the same way that with kinematics we express the velocity, acceleration, and displacement in terms of time, we'd prefer to write with simple harmonic motion, we'd also like to have our equations in terms of time. So that theta is going to have to be switched over to time. But of course, theta doesn't equal time. We need a relationship, and we need to develop a relationship between the two. So let's try to do that. Now, if our object rotates through an angle theta, then theta out of a full rotation, theta is a fraction of a full rotation. In other words, it's a fraction of 2 pi. Now we have uniform circular motion, and that means that our object is moving at constant speed. And that means that however much time it takes to go from here to here, that will be a fraction of the total time to go once around, which we call 1 period. In other words, theta has to be to 2 pi as time is to the period. So these two ratios have to be the same. And that means that theta must be equal to 2 pi t all over the period. And you might recognize 2 pi over t is just omega. It's the angular frequency, which means that theta can be written as omega t. So that omega is becoming more important all the time. And we can do a brief check to see if that argument is really working. The angle theta after 1 period should be equal to 2 pi. Let's check if that's true. So when t equals 1 full period, so t is going to be replaced by a full period, then of course I get 2 pi. That checks out. What should theta be after 1/4 of a period? Well, we're expecting that 1/4 of a period, we should get theta being equal to pi over 2, 1/4 of 2 pi. Let's check that out. That checks out as well. So that means we're ready to write our displacement equation of motion. So our version in UCM was y equals r sine theta. In SHM, y becomes the displacement, and r becomes the amplitude, and theta becomes omega t. So that equation will tell us the displacement of an object in simple harmonic motion as a function of time. We want to now get the equations for velocity and acceleration as a function of time. So our velocity is going to be sinusoidal, just like the displacement. It's going to range between a maximum value and a minimum value. So V naught is really the maximum speed. And we know that the period is once again going to be 2 pi. It's got to be the same in every way, except that our displacement was originally 0, right? We had theta equals 0. Our original displacement, our y value, was 0 when we were right in the middle of the motion, when we were in equilibrium position. Now, the speed here has to be exactly the same as the speed right here, because we know that the particle in uniform circular motion always parallels the particle in simple harmonic motion. So whatever our speed was in uniform circular motion, that's going to equal our maximum speed, or V naught, our maximum speed in simple harmonic motion. And so we're starting at t equals 0 with a maximum speed. And then we're just going to trace it out. So it'll go from a maximum here, 0 speed at the endpoints. So it goes from maximum speed in the middle, 0 speed at the endpoint, maximum speed in the middle, 0 speed at the endpoint, maximum speed back at the middle again, and restarting the cycle. So the equation of the graph I just drew, you can see that's a cosine function. And our velocity would equal that maximum velocity times the cosine, and I'll have exactly the same argument, omega t. We were just saying that the maximum speed for simple harmonic motion is equal to the uniform speed for the uniform circular motion. Here's my mass, which is shadowing the particle on the circle. Whatever the speed is in uniform circular motion will be exactly the same as that maximum speed, which is obtained in the center of the motion between the two endpoints. What we want to do eventually is we want to rate that maximum speed in terms of omega and our amplitude or maximum displacement. Well, in general, we always know that speed is distance over time. So let's apply that to find this uniform circular motion speed. For a distance, I'm going to choose the circumference of the circle, 2 pi r. Because I know if it goes around the circle once, the amount of time it takes is 1 period. And then I can notice 2 pi over t is the same thing as omega. So I get that this speed is equal to omega r. Of course, r has got to equal the amplitude in the simple harmonic motion, so that I get this expression for my maximum speed in simple harmonic motion, which will be omega times x naught. And that turns out to be quite useful. So in summary, my equation for my velocity in simple harmonic motion will be omega times the amplitude times the cosine. Okay, let's try to look at the acceleration now as well. Accelerations are a little bit easier because we can say right away that acceleration by the defining equation for simple harmonic motion has to be this. And we just worked out what the displacement vector was. So we already know that A has to equal negative omega squared x naught sine omega t. So we've got our equation right there, already done. And whatever goes in front here, that's always the amplitude of a sine function. So that means that's really my maximum acceleration, right? So my a naught, this is my maximum acceleration in magnitude, is going to equal omega squared times my amplitude. Okay, so just summarizing those three equations, we had x equals x naught sine omega t. Okay. So there's the three equations that we just determined. They can be derived really easily with calculus using derivatives and the chain rule. So I know that if I start with x equals x naught sine omega t, then v must be equal to the derivative of x with respect to t. Now the amplitude's a constant. The derivative of the sine function is the cosine function. Keep the argument the same, use the chain rule. The derivative of the argument is omega, so I've got to multiply by omega, so I get omega x naught cos omega t. And then I can take it one more step, do exactly the same thing. A will equal dv dt. The acceleration is the rate of change of velocity. So these two out front are constants. Derivative of the cosine is the negative sign, and the derivative of the argument is omega, so I do get negative omega squared x naught sine omega t. So it's much faster with calculus. And just to summarize those maximum values, we had x naught equals x naught. We had v naught equals omega x naught, and we had a naught equals omega squared x naught. So we're just multiplying by an extra omega every time. Let's try a few numerical problems now. So read over the question, see how far you can make with it, and then come back for the solution. Okay, so hopefully you said that if you lift an object by 15 centimeters from equilibrium, it will oscillate between two extremes 15 centimeters away from equilibrium. And that means your amplitude here would be 15 centimeters. Next, you're asked for the maximum speed. So V naught is equal to omega times x naught. But we don't know omega directly, but we know that for a mass spring system, omega is equal to the square root of k over m. So this will equal the square root of 5 newtons per meter divided by 0.2 kilograms, and that works out to be the square root of 25, or 5.0 rads per second. So now we can get that maximum speed. It's going to be equal 5.0 rads per second times 15 centimeters, giving 75 centimeters per second. And now let's get the maximum acceleration. That'll be omega squared times the amplitude. So that'll be 5.0. Now remember that radians are really dimensionless. So let's look at the units on this one. We've really got 5.0 seconds to the minus 1, all squared, multiplied by 15 centimeters. That gives 375. And the units will be centimeters, and the seconds to the minus 1 gets squared, so that's times seconds to the minus 2, or centimeters per second squared, which you should recognize as being a proper unit for acceleration. And we should not keep so many significant digits here. Okay, so the equations that we derived were for a mass spring system. You started the object in equilibrium and you gave it a push to the right. And then you got these equations here. What I'd like you to now do is to find the equations if you were to give it different initial conditions. So in the first case, I want the case where you started at equilibrium, but you give it a push to the left. And then start it from an endpoint, say the right endpoint, and let it go to the left. And in the third case, you'll start it from the left and let it go from rest. So stop the video and try that now. So hopefully in the first case, what I'll do here is just very quickly draw sketch graphs for the displacement. So in the first case, you are starting it from equilibrium, but you're giving a push to the left. So you're going to get a negative sine function. In the second case, you're starting to the right and you're letting it go. So in this case, you're talking about a positive cosine function. And in the third case, you're starting from the left and letting it go. So you're talking about a negative cosine function. So in the first case, we've got x equals x naught. That never changes. But this time, it'll be a negative sine function. Argument always stays the same. Second case, it's a positive cosine. And the third case, a negative cosine function. And then, of course, the quickest way now is to use calculus to get the other equations. But basically, anytime you take the derivative of a cosine, you'll get a negative. So this one's already negative. Next one, derivative of the cosine becomes negative. And in the next one, derivative of a cosine becomes negative. So you're going to end up with a positive on that one. And then for the accelerations, fast way is you're always going to get omega squared x naught as your maximum acceleration. So you can write that in straight away. And then you've just got to take the opposite of your x vector. So if this one's negative sine, the other one's going to be the acceleration will be a positive sine. This one's a positive cosine, so we'll get a negative cosine. This one's a negative cosine, so we'll get a positive cosine. And another question. So take some time to read it over. Pause the video, try this question now. Okay, the period of the motion, it takes 10 seconds to start repeating itself. So t is equal to 10 seconds. B, the amplitude, that is simply this distance here, which is 6 meters. Part C, the maximum speed, v naught equals omega x naught. We can get omega from the period. Remember, if you know period frequency or angular frequency, you know all three. So this will be 2 pi divided by 10, which is 0.63, and that'll be radians per second. Part D, they're looking for a general expression for the velocity in terms of time, but we should put in as much numerical information as we can. I'll write down the displacement equation first. This is one that is a cosine function. So it's a cosine omega t, a positive cosine function like that. So the derivative of that will be, and we can just write it in terms of the maximum speed. Derivative of a cosine is the sine, and we'll get that expression. And we forgot to work out what the maximum speed was, so it should be 0.63 radians per second times the amplitude of 6.0 meters, and that gives us a value of 3.8 meters per second. So we can put that into this equation, negative 3.8 times the sine. Omega we now know it's 0.63. And t we leave as a variable. So this will tell us the velocity at any time t. And finally, we want to get the maximum acceleration, e, which would equal to omega squared times the amplitude. So that'll be, our omega was 0.63. That'll be seconds to the minus 1, getting squared, times the amplitude, which was 6 meters. And when we multiply that out, we get 2.4, and that'll be meters per second squared as the maximum acceleration. And that's all for today, folks. Thank you very much.